we were talking about the greenhouse effect and about how different kinds of light affect molecules. So we're going to go back to that. And then we are going to look at how to model molecules as well. Okay, so this was something that we had looked at in the previous chapter on how different kinds of molecules affect or how different kinds of light affect molecules. And we focused mostly on ultraviolet light, but different kinds of light can do different things. X-rays can cause electrons to be ejected. They can also break apart molecules. Should I turn out the light in front of this so would it make it easier to see? Yes. Okay. Ultraviolet light and X-rays can also break apart the molecules, depending on how strong it is, A, B, or C UV light. So UVC can break apart molecules, UVB can break apart weak molecules, UVA is going to do like visible light, which would be if there's an electron, it can cause it to move around within the molecule, but not really do much else. That's just what makes us see color. So if it's absorbing a certain color, we'll see the other colors. Let's see. The one we are focusing on is going to be IR light. So IR light will cause the molecules to vibrate. Okay, so vibration is motion. Motion gets translated to heat. So the more vibration that we have, the more that molecule is going to warm up the molecules around it. It's going to bang into those molecules, cause them to move around. Now we also have microwaves on there. You all have used a microwave oven. Microwaves also cause motion, but they cause rotations. Now, if I have this happening in the air, not much is happening other than it moving around. But if it is in a liquid and one molecule is trying to turn, it's going to bump into and drag along other molecules. And again, that motion gets translated to heat. And that's especially effective with molecules like water. Okay, so we are going to be looking at, in particular, molecules that we find in the atmosphere. So the one on the far left is 3 reds, which is 3 oxygens. So what is 3 oxygens? O3. Molecule from last chapter. Ozone. Ozone. So that's our ozone. And so this is again illustrating that that ultraviolet light can break that bond. The ones here and here, the middle and the right-hand side, are supposed to represent carbon dioxide, with the one in the middle being kind of a dark gray. Oh, I'm sorry. No, the one on the far side is water. So the one in the middle is carbon dioxide. So it's got this dark gray black atom for the carbon. And so the infrared is causing the bonds to do this and also to stretch outward. Molecules have different kinds of vibrations. We'll look at that in a little bit. So we classify them by symmetric or asymmetric stretches. So symmetric would mean they're both going out and coming in at the same time. Anti-symmetric would mean one is going out while the other one's in. So you have this motion going on. Okay, and those are affected by light differently. So something that is symmetric is much less likely to absorb IR light than something that is anti-symmetric. Okay, and then some molecules have what are called asymmetric, which means that there's no symmetry to it all. It's just disorder. All right, this one has the oxygen in the middle, and I thought these were the dark gray, but that's supposed to be white that is lightly shaded. So this is actually water, and it's showing it rotate. Okay, so those are the 3 that we really need to know. Ultraviolet, infrared, and microwave. What can they do to molecules? All right, so for infrared light coming from the sun, if we look at these red arrows as being the infrared light, light from the sun is called radiation. So there are three types of heat transfer. If you are an education major, this is something you might have to teach your kids, three types of heat transfer. One is radiation, a form of light, and that radiation might come down from the sun. It might be absorbed by molecules in the air, as this one is, or it might be absorbed by the ground. Okay, once it gets there, then we have conduction. So let's think about the air first. Conduction would be like the molecules, or sorry, let's think about the ground first. Conduction is when things are actually touching one another. So the hot molecule bumps into a colder molecule and it heats up the one next to it. Okay, so conduction is the molecules bumping into each other. It might be the air molecules bumping into each other. It might be the ground bumping into each other. It might be the air bumping into the ground. All of these things, the molecules bumping into each other is conduction. So if we think of like a hot pan, it is thermally conductive, heat conductive, if you touch it, right? Now, if you have your hand close to the pan, but you're not actually touching it, you probably feel the warmth of it, but you're not going to burn yourself. Okay, so that's radiant heat that is coming off of it. But if you're not actually touching it, then it's not convection. And then the last kind is convection. Convection means stirring or mixing. So this is more appropriate to think about the air. The warm air expands. The molecules are moving faster, getting farther away from each other, so they're less dense. And so they move up, and the colder air, which is more dense, starts sinking down. And so you get warm air rising, cold air falling, and that's mixing of the air. Okay. So three kinds of heat transfer: radiation, conduction, and convection. And this doesn't just apply to radiation from the sun or IR light. This is all kinds of heat transfer pretty much fit into these categories. So I've got the heat coming off of the ground and mixing up with the air there. So that's our convection. Okay, so let's think about the molecules. The bond, sometimes when we make molecules, and we're going to be making molecules here in a minute, we'll use a stick to represent that bond. But really, the nuclei can move further apart and closer together. And so it acts like a spring. And that's what gives us our vibrations. So a diatomic molecule, so di means two, it has two atoms. Diatomic molecules have only one bond. So this might be with the blue, it might be nitrogen, N2. And so that bond vibrates. And it turns out that they have certain preferred frequencies. We call these resonant frequencies, that if it's bumping around and vibrating all on its own, it's going to settle into this one frequency. Okay. Each kind of stretch, and then we'll also talk about bends in a minute, is going to have its own frequency that it does. Okay, so really there's only one thing that oxygen and nitrogen can do. That's 99% of our air, oxygen and nitrogen, only one thing it can do. But if I have more bonds, then I have more possibilities. So this is our carbon dioxide, and A, where the both of these are going out, that's our symmetric stretch. And B is our anti-symmetric stretch. Okay, so it has those. But because there are three molecules, it can also bend. So if we think about this coming down while those two go up, it can kind of go from a straight line to a V, right? Technically, it can do that up and down and in and out. As far as the molecule is concerned, it's the same in every direction. So it kind of looks the same to hit, but it can do those things. But these two would be what we call degenerate or the same for that molecule, because from the molecule's perspective, it just looks the same. Okay, so we have bends, we have stretches, we have preferred frequencies. And when we went from 2 atoms to 3 atoms, we went from 1 vibration to 4 vibrations. Okay, so the more atoms we have, the more possible vibrations there are. That's going to be really key. Now, the next thing we're going to talk about is called heat capacity. So if you think of your capacity for something, it's an ability or the amount you can hold. So heat capacity is like how much energy can you put into this thing before it changes temperature. Now, it's not really like, oh, I'm collecting energy and now I change 1 degree. It's changing a little bit at a time. But each material requires a different amount of energy to change temperature. So if I look at gold, this is 0.12 or 1.3 if you round it. It only takes a tiny bit of energy to warm it up. So if you've ever had a gold necklace or a gold bracelet, or touch something that is gold, it probably feels cold right away, but pretty quickly it stops feeling cold because it doesn't take a lot of energy from your skin to warm it up. But if you have something like iron or aluminum, that continues to feel cold for a little bit longer because as you're holding it, it's going to take more energy to warm it up in order for that to be the same temperature as your skin. So this is all based on the grams that you have, but we know because of molar mass, not every element weighs the same. So aluminum is almost 1 per gram, but 1 gram of aluminum has a lot more atoms than 1 gram of iron. All right, so we can also do what we call molar heat capacity, and then we're comparing how much energy per atom that we have. So those are just two different terms talking about the different ways we can look at it. Okay, so these are mostly metals. We do have graphite, which is carbon in here. We have some compounds. So water is the highest among these. Now it's not the highest ever. So if we have something like glycerol, that's pretty high. I think that's higher than water, but it doesn't get a lot higher than about 4 or 5. This is one of the highest heat capacities. And this is why if you get a burn on your skin, you're supposed to run it under cool water because the water can absorb a lot of the heat from your burn before it changes temperature. Even if you're just soaking your hand in water, the water is still going to absorb a lot of that energy. Unlike if you just put aluminum foil on it, that aluminum foil is just going to heat up right away. The water's going to stay pretty cool. It's also why we cook with water, because when we heat the water up to boiling, which can take 10 minutes or so to get all that energy in there, that's going to push a lot of heat into the food without changing the temperature of the water. And that means when I put my casserole on the dinner table or my turkey at Thanksgiving, it's going to stay warm for a while. It's not going to dissipate that heat out into the room because all of the moisture in my turkey, all of the moisture in my casserole is mostly from that water and has a high heat capacity. So it would have to lose a whole lot of energy before it would change temperature. So that's really beneficial to us in some practical ways. Also weather-wise. So the coasts like Florida, New York, California, their weather extremes are much less than in the middle of the country. So if I'm looking at someplace like Kansas, that's in the middle of the country, no large bodies of water nearby, the coldest part of the winter can be well below 0, and the hottest part of the summer can be well above 100. But if I am looking at someplace on the coast, generally I stay in narrower bounds. So I'm not going to get much into the 90s, maybe a little bit in the hottest parts of the summer on the East Coast. And it doesn't get as cold as it does. It might snow, but it doesn't snow as much as it would in other parts of the country. Of course, there are some times when it's too cold. That's another story. If you look at California, my brother went to school out in California, and it basically was between like 50 and 80 all the time. So it didn't get extremely hot. It didn't get extremely cold. Okay, so water helps the air temperatures kind of moderate themselves. All right, and then we have some solid materials. Wood, cement, glass, and granite, they're not pure things. They're made of mixtures of things. And so this is going to be dependent upon, well, how much of that cement is made up of limestone and how much of it is made up of silica and that kind of thing. But these are some approximate numbers. Okay, so let's put all of that together with our air. If we look at the heat capacity of things that are normally in the air, nitrogen makes up about 80% of the air, so it makes sense that the heat capacity of the air is pretty similar to nitrogen. Oxygen is also pretty similar to nitrogen, makes up most of the rest of it. And then our third most abundant part of the air is argon. Argon is much lower. Why would argon be so much lower than the others? Where is argon on the periodic table? It's one of the noble gases. So if we look at this formula, there's only one atom. If there's only one atom, does it have any bonds? No. With no bonds, it's not vibrating. All of that heat capacity is just from any kind of light that might be absorbed to move around the electrons or it bumping into things. So it has a pretty low heat capacity. Okay. Carbon dioxide, on the other hand, is quite a bit higher. And the reason why it's quite a bit higher is it has more bonds, and with more bonds, it can do more kinds of vibrations. Now, some of the other things that might be in our atmosphere, of course, water might be in our atmosphere. It's got a pretty high heat capacity. We already know that. Now, this one is per mole instead of per gram, so that's why the number is a little bit different. This is methane. So methane, sometimes we think of these as being cow farts. Natural gas is methane. It's really more commonly from the burps of cows as they chew up their grass and their cud and those kinds of things and partially digest it. Methane is produced, and so they'll burp, and this gets released out into the atmosphere. So those are all pretty high. The ones in orange are what we call greenhouse gases. So they absorb enough energy, they have a high enough heat capacity that it helps to keep the earth warmer. Now, remember, if we didn't have any of them, the earth would cool way off. It would be this frozen block of ice, okay? So having some of them is what keeps the earth habitable. So if we look at some place like Mercury, so Mercury is right next to the sun, it is also phase locked with the sun, which means that the same side of Mercury always faces the sun, that it doesn't rotate and have day and night. It's like, depending on where you are, it's always day or it's always night. So the part that's always day has extremely high temperatures, and the part that's always night has extremely low temperatures because there really isn't much of an atmosphere on Mercury, so there isn't anything to absorb that energy. All right, so the greenhouse gases, we know they absorb that infrared light. That infrared light causes them to vibrate, causes them to move around more and heat up things around them. They hit the other molecules, make the other molecules move. And so as they mix, which is convection, and as they bump into each other, which is conduction, they're causing that heat exchange, which warms up the whole atmosphere. All right, and then the ones that have the black numbering, they can't hold as much energy. So they emit the IR light, or the IR light just passes right through it. Okay, so it doesn't really cause a change in them. For reasons I'm not going to go into, IR light is best absorbed by molecules that are polar or can be made polar. And so to understand how we know whether or not something is polar or can be made polar, we need to think about the dot structure. So we're going to do that in just a second. I got to make sure. Okay, I did want to go through this next slide. Okay, so we mentioned several greenhouse gases. All of these can be greenhouse gases to a certain extent. If we look at this diagram, this has a bunch of those greenhouse gases, and it has CO2 is making up the most of these. But water is left off that list. So I'm going to put this one up. Water vapor makes up 95% of the greenhouse gases. But our planet is 75% water. we can't really affect the amount of water in the atmosphere very much because there's so much there already. On the other hand, we have a little bit more control over some of the other ones. All right. So let's go back and look at some of the other ones. Ozone, we know we don't want to get rid of it altogether because it's protecting us. We don't want to really be creating it down here because that's going to be something that's going to affect our lungs and be bad for us. N2O, that is laughing gas. It's a byproduct of some things that are man-made. We can do some things to control it, but it's a smaller portion. So here's carbon dioxide is much of what's in the atmosphere. N2O is pretty small. Methane's a little bit bigger, and then we have these other smaller things. HFCs, those were the things that replaced chlorofluorocarbons, CFCs. So the HFCs, instead of chlorine, they have hydrogen on them. So we don't have those random chlorines around breaking up the ozone. But with the hydrogen attached, it absorbs more energy and so is acting as a greenhouse gas. All right, so these are the big ones. And I think that's somewhere in your notes that it asks you for major greenhouse gases. So we talk a lot about carbon dioxide because that makes up so much of the greenhouse gases. It's a much higher percentage than the others, but there are others that are significant too. And we try to control those as well. All right, so we are going to look at a few specific molecules. And first we are going to look at their dot structure, and then we are going to try and build them, and then talk about how we know if they're polar or non-polar. So what I want you to do, I will write down the formulas on the board, and then we will try and build the dot structures. All right, so the first one is CO2. And remember, the first thing we want to do is to count the valence electrons. All right, so how many valence electrons does carbon have? So 4. So remember that we're going to look at the periodic table, and we can do 2 ways. We can find carbon and then count over from the side how many elements there are, skipping over the transition metals. So 1, 2, 3, 4. That's one way. The other way is if you have one of these that have the numbers at the top, carbon is in column 14, so you just subtract 10 from it. So 14 minus 10 is 4, so it's 4. Okay, so we've got 4 for carbon. How many for oxygen? 12 total in this case. 6 for each of them, because same logic, so we count over and it's the 6th one. But because there are 2 of them, we have to count the electrons for both of them. Okay. So total, we're going to have 16 electrons. So take a second to try and count the valence electrons for each of these. All right. So water, I think we've done before. Did you get 8 for that one? Okay. Ammonia, nitrogen has 5. And then we have 1 for each of the hydrogens. So that's going to be 8. And then we have 4 for the carbon, plus 1 for each hydrogen, again gives us 8. Okay, so 8 should remind us that we have this thing called the octet rule, that other than hydrogen, the atoms want to have 8 electrons around them. And we're going to use dots to represent those electrons. Let's look at the methane one first, and we will save this one for last. So our rule is if the first element is not hydrogen, we'll put it in the middle. We don't put hydrogen in the middle because it can't form 2 bonds. So we're going to put carbon in the middle, and then the other ones go around it. So we don't make a row, we make a circle. And so on your quiz, if I see people making lines instead of circles around the, or boxes or whatever around the atoms, you're not going to get points for that. Okay. The next thing we do is we form a bond. How many electrons are in a bond? One bond, two, okay? So if I put two dots between the carbon and the hydrogen, that's one bond. So I'm going to do that all the way around for each of these. And then I'm going to count how many electrons I have. Well, wait, no, I have to complete my octet first. So my octet says hydrogen only needs two, and hydrogen does only have two in each case, so it's good. And then everything but hydrogen should have 8 dots. So does the carbon have 8 dots around it? Yeah, okay. Now I'm going to compare the number of dots to my valence electrons. Do I have 8? Yeah. So this is a good dot structure, all right? Okay, now try the same thing with ammonia. So this is one I don't think we've done yet. See how you get with that one. Nitrogen's going to go in the middle, and the hydrogen's around it. So when I get this far, does nitrogen have 8? So it starts with 5 valence electrons, but when I form the bonds, it still only has 6. So I have to complete the octet. Oops. I have to complete the octet by adding 2 more electrons. All right, so those 2 electrons are called either a non-bonding pair or they are called a lone pair, right? So I will probably always call them a lone pair, but you'll also hear of non-bonding pair. That's going to be really key for us understanding the shapes of the molecule. All right, so do water and figure out how many lone pairs are on the oxygen in water. Now remember, even though the hydrogen is listed first, hydrogen won't go in the middle. So that's the only time we don't use the first atom in the middle. All right, so to have 8 electrons around oxygen, I had to put 4 extra electrons, but how many pairs are there? How many extra pairs are there?
2 extra pairs.
2 extra pairs. So we would say there are 2 lone pairs. All right, then for carbon dioxide, we have a different situation that we run into. When we compare the total number of electrons after we add the octet, it's not going to be equal to our amount. So go ahead and get started on the carbon dioxide, see what you come up with. Remember, carbon's going to go in the middle because it's listed first. The other way you can do it is whichever one's farthest from fluorine on the periodic table, but I find it easiest whichever one's listed first. Okay, so we said carbon dioxide was supposed to have 16 valence electrons. That's how many we counted here. But if we give every atom an octet, and remember the bonds, they get to share the electrons. So these 2 count for both the oxygen and the carbon. How many dots do I have on that structure right now? 20. So it's too many dots. When I run into that problem, what I'm going to do is I'm going to take away dots from the central atom and one of the atoms next to it. Don't take away bond dots. We don't want to remove bonds. We're going to add bonds. So we're going to take away those 4 dots and replace them with an extra bond. So this is now a double bond instead of a single bond. All right, that gets us down to 18 electrons. So we're going to have to do it again. And it'll look like that. Okay, so I'm going to double check. 2, 4, 6, 8, 10, 12, 14, 16, which matches here. This oxygen has 2, 4, 6, 8. This carbon has 2, 4, 6, 8. And this oxygen has 2, 4, 6, 8. So everybody's happy.